right, we're going to look at our answers for the Chapter 6 lab. Mostly this was just about, of course, using the unit normal table. Mostly you probably didn't have much problem if you sketched what you were looking for and then just carefully used the tables. But so 8 says, find each of the following probabilities for a normal distribution. And 8a says, what's your probability of, what's your probabilities or proportions, same idea here, above a z of 2.25. All right, so it gives us a z of 2.25, and it asks us, oops, what's above it? So again, that just is cluing us in that we want the tail. So the proportion here is 0.0122. For B, it says, what's the proportion above negative 1.20? So we'd get a negative 1.20, and it says, what's above it? Oh, well, that's the body. So we use the body column for that. So for 8B, that proportion is 8849. C asks for the proportions below a z of 0.40. Again, we go to a z of 0.40. It's almost a half of a z. And it says specifically it wants below it. So that's another one where we're looking for the body column in the table. So for 8C, the answer is 0.6554. And then lastly for D, doing the same thing here, it's negative 175 and what's below it. So that's going to be almost like this one, but in the tail because we want to know what's below it. So that's 0401. So those are the answers for 8, those 4 parts there. 12 is basically having you do the same thing, but using the table. But now specifically all of these are relative to column D, the distance between a mean and a z-score. So for 12, it says, find the z-score boundaries that separate the normal distribution as described in each of the following. And A says the middle 20%. Well, again, if we're going for the middle 20%, but remember our table, a little asymmetrical here, our table for D can only go from the mean to a z. So we can only get half of it at a time. So we've got to split this in half, the 10% on the left and the 10% on the right. Then, of course, remember the table doesn't work in percentages, it works in proportions. So what we're looking for is the z-score that separates our, the mean, the bottom 10%, what z-score goes here and here. So we're looking for p's of 0.1000 on each side. Get them both, and then you've got to add it together because it's asking you what the total amount is. Get the left side, get the right side, add them together. When you do for 12a, you should find that your z values are positive and negative, one on each side, 0.25. And then it's literally the same for all 4 of them. B is the middle 25%. So again, we've got to cut that in half. 12.5% on one side, 12.5% on the other side. So for 12B, we're going to be plus and minus 0.32. C is looking for the middle 70%. So again, 35% and 35%, cutting it in half and then putting it back together. 1.04. And our last one is the middle 90%, so that's almost all of it, right? That should be a pretty big number there. So for D, 45% and 45% on each side, we get a Z of plus and minus 165. There's 12. Next up was question 16. Parts A and B. 16 says, in the year 2004, New York Yankees had a batting average of 245. Of course, the batting average varies from game to game, but assuming that the distribution of batting averages for 162 games is normal, with a standard deviation of 40 points, answer each of the following. A, If you randomly select one game from 2014, what is the probability that the team will have a batting average over 300? So this is a problem like what we saw in lecture, where the first thing we're going to have to do is we used an IQ score as an example, take our raw scores and turn it into z-scores so that we can use the table. So what we know is that from this problem that, for our z formula, sample mean minus population mean over standard deviation. Well, here we have, oops, am I looking at the right spot? Yes, if our raw score is 300, so that's the sample mean we're looking for, 300 or higher, right? What's the odds of someone getting that score or higher? So we need to know what z-score that is to look above it. And then the population mean was 245, and the standard deviation it told us was, where is that, 40. So the z-score equivalent for a score of 300 is 1.38. So once we know that, it's just asking us the same old question again. If we have this normal distribution, what is above a 1.38? So it's asking us, what our randomly draw one game, what's the probability? So we could probably report this as a percentage. For me, I'll always be clear if I want it percentage or not, but it sounds like they're looking for a percentage here. So what percentage of scores is above 300 is the same thing as saying what percentage of scores is above a z of 1.38. And the answer to that is 8.38%. So what are your odds of going into that season and pulling out a game where the average was 300 or more? 8.38%. B is doing the same thing. It says if you'd randomly draw a game, what's the probability of pulling the one where the batting average was under 200? So the same thing, we have to turn the 200 into a z-score. When we do that, it's a z of negative 1.33, right? So this is the other side, but negative 1.33. It's negative because we're below the mean, right? And so it wants to know what's below that. So what proportion or what percentage in this case is below a z of negative 1.33? And the answer, this percentage is 12.92. If in your own doing this, you reported them as the raw probabilities, that's fine for this. The key is knowing how to convert it to z's and then look it up in the table. So that's question 16. And then lastly, question 20. Says a recent report indicates that 2-year-old children from well-educated suburban families watch an average of 60 minutes of television each day, assuming that the distribution of television watching times is normal, with a standard deviation of 25 minutes. Find each of the following proportions. A, what proportion of 2-year-old children watch more than 2 hours of TV a day? So this is just like what we did. We've got to take basically our raw data and turn it into z-scores and then look it up in the table. So what we find here is if the mean is 60 minutes and the standard deviation is 25 minutes, this says what proportion of kids watch more than 2 hours? Well, remember we're talking minutes and the question put this in hours, so we need to put that in minutes. 2 hours, 120 minutes, right? So we do the same thing. We have to turn 120 minutes into a z-score. So 120 minutes is the sample mean we're looking for. The population mean was, I keep losing it, 60 minutes. And the standard deviation is 25. So when we do that, watching TV for 2 hours at that is the same as a z-score of 2.40. So now, it's the same old question. Oops, 2.40. How much of the curve is above a z of 2.40? So we find there that the proportion 0.0082. So in other words, less than 1% of the kids from this group watch more than 2 hours. And then the other way around, what proportion of 2-year-old children watch less than 30 minutes, a half of a standard deviation? Put your 30 minutes in here instead of 2 hours. 30 minus 60 divided by 25. Again, it's going to give us a negative, so we've got a z of negative 1.5, or I'm sorry, 1.20. Same old question, what proportion is below that negative 1.20? So again, it's a tail. And here the proportion is 1151. So just over 11.5% of the kids watch less than 30 minutes a day. Those are the answers to Lab 6. You know the drill by now. If you need more help than that, reach out to me and let me know, and I will do my best to help you. We'll put the answers to Lab 7 in a separate video